Okay, we'll have a talk by Kristina Punzi on the high-energy substellar boundary, a study of the relationship between X-ray luminosity and the presence of disks.
Okay, so the last talk gave a little preview of what I'm going to be talking about. So I just finished my degree at RIT, and I just moved down the road at Wellesley College. So if anybody is interested in talking to undergraduate women in astronomy, please talk to me. Let's see. So why do we want to do this work? We want to characterize X-rays from young low-mass stars to understand the timescale and conditions for exoplanet formation. So we want to provide everybody with information about spectral and temporal parameters so they can be incorporated into stellar irradiation models and disk evolution models. So we all know, I don't have to really stand on my soapbox here, but we all know that low-mass stars right now are pretty much our targets for the discovery of potentially habitable exoplanets. And I say potentially because they have high levels of activity, so that might be a hazard for habitability. So there's a lot of these objects, about 75% of the stars within 10 parsecs. And they have a low luminosity, which means they have close-in habitable zones. And because we're looking at objects in nearby young moving groups, direct imaging of planets that could form around these objects could be easy, comparatively. So there hasn't been that much talk about nearby young moving groups or young objects this week. So the TW Hydra Association, which is our very close friend, is at a distance of about 50 parsecs and an age of 8 million years. So it makes it a really good laboratory for studying these really young objects. And so the age is also similar to the timescale for giant planet formation. And it's the only young cluster that's close enough to get disk masses from ALMA and to get X-ray luminosities from Chandra at the same time. So we see that most members earlier than M3 lack disks already at this age. So does that mean they've already formed planets, or will they never form planets? So in a preliminary study in 2016, we looked at the archival X-ray data that was available for all of these, for as many members as we could find in the TW Hydra Association. So we looked at ROSAT, XMM, and Chandra, and that's what I'm showing. Ooh, what did I, where's the, oh, separate laser pointer. Okay, so this here is a plot of our sample from 2016. This is M spectral subtype versus X-ray luminosity. And this black line here is the XMM Newton extended survey of Taurus. And then these are 1 sigma dashed lines over here. So the pink is ROSAT data, the red is XMM, and the green is Chandra. And we've got some upper limits over here. And the filled-in circles means that there's evidence for dust associated with these objects. And the open circles means that there is not evidence for dust. So we find that these early M stars are overluminous, and that these late M-type objects are underluminous. So we're missing kind of some objects over here. So is this a real trend? And if it's a real trend, does that mean that X-ray luminosity declines more rapidly for late M, around this M4, M5 spectral type? So what could that be from? Maybe suppression of coronal X-ray activity by accretion, or a fundamental difference in the internal structure of these objects. So our combined submillimeter infrared and X-ray data showed us that there's an anti-correlation between pre-main sequence X-ray luminosity and disk lifetimes. So the evidence for residual primordial disk material increases for these later spectral types. They hold on to their disks a lot longer, according to the infrared and submillimeter data. So this might mean that disk survival times may be longer for ultra-low mass objects. And right now, the current understanding is that evolutionary models predict that there really isn't that much dependence on stellar mass. So this could be really important. So what we did was that we conducted a Chandra Cycle 18 large program to expand our sample because we were really missing objects in this lower mass regime. So we had 10 mid to late M-type stars, and they're candidates or confirmed members of the TW Hydra Association. So the information about our targets are over here with their spectral types and information about their disks and our exposure times. So we had about 10 samples, or 10 new targets, that more than double the number of targets we had in this regime before. So now we have equally represented samples of the early M to and mid to late M spectral types. So now we can get some better statistics. So here is the plot. This is the same plot I showed you before, but our earlier sample from 2016 is represented in black, and the new sample is represented in red. These weird ones with the lines are two separate observations, but one was flaring, and the object is not flaring in the other observation. So I just represented them as a line. So what you can see here is that the trend appears like it's real. So we still have some upper limits over here. And the disk fraction for early M's is about 2 out of 20, so still no evidence for disks, really. So they're zapping away their disks. And after, in these later spectral type regime, you have a lot more disks. So they're holding onto their material for a lot longer. So that's really interesting. But what I decided to do was put this information on an HR diagram and see what it could tell us about the objects themselves. So effective temperature is on the X, and the Y is bolometric luminosity of these objects. These are Baraf 2015 isochrones. And the one on the top here is 1 million years, and the yellow here is 20 million years. And then these are pre-main sequence tracks. I've highlighted the hydrogen burning limit, 0.08 solar masses. So I've also coded my objects with X-ray bright and X-ray faint. So the pluses are X-ray bright objects, and the circles are X-ray faint objects. So we can see that there's two groups here on the HR diagram. So this observed drop that we see in X-ray luminosity may be able to predict the substellar boundary, and without relying on evolutionary models. So this could be really powerful. They could be telling us what type of objects they're going to be in the future at this early of an age, which could be really powerful. So why are they why is the X-ray luminosity dropping off? So is this a result of different fundamental processes that's happening, nuclear fusion eventually, that hasn't happened yet, or electron degeneracy? And this drop might be able to tell us something about the topology of the magnetic fields. So assume you have a very complex magnetic topology for these type objects over here. You might observe a larger value of X-ray luminosity. And if you have a less complex field, you might observe a lower value of X-ray luminosity. But the issue here is that there really isn't that much information available right now about the magnetic topologies of these very, very low mass pre-main sequence objects. And I'll just what happened? There we go. And I'll just point out here that all of these objects over here will probably never form stars. If you look at the pre-main sequence tracks here, they'll probably all just cool to be brown dwarfs. So this observed drop in X-ray luminosity might be able to tell us something about the stellar-substellar boundary at this very, very young age without relying on these evolutionary models, which we've heard there might be some issues with. You might not be able to trust them at this moment. They still have to be tested a lot more. So this could be a really powerful tool, and it might allow us to infer something about the magnetic fields, and we might be able to use this as a diagnostic of what type of objects, what these objects might be, if they might be stars or brown dwarfs in the future. So please, if you want to help me with this, please get some information about the magnetic fields of these objects and try to tell me by the next cool stars. And contact me if you have any information and would like to talk.
Okay, we have time for a few questions. Right over here.
Hi, Marina Kunkel, Western Washington University. So looking at this diagram, there are a few crossover objects that do cross the line. Can you say anything about them?
I'm not too sure yet. I don't remember which objects those are exactly. But I'm guessing, it's been a while since I've looked at them, but it could be that they're experiencing a flare at the time or not flaring at the time. It's a little messy towards that boundary, but I think we can see two distinct groups, but it would be interesting to get more observations of these stars over a longer period of time.
Yeah, Jeff Linsky, University of Colorado. There's at least two very interesting things that might be happening here. First of all, in the late stars, you mentioned they still have disks, and the interaction between a magnetic field and the star and the disk would encourage strong X-ray emission, which you don't see. That's one effect. And the other is, as the stars become less luminous, convection is much less vigorous, and convection essentially is very important for messing up the magnetic fields, leading to magnetic field annihilation, and that would lead to X-rays. So the loss of convective energy, or decrease in convective energy, may be what's driving the decrease in the X-ray flux for the late-type stars.
More? Another question?
Yeah, actually, I like Jeff's idea. I wanted to point out that the interiors of these things don't have any idea really whether they're going to be brown dwarfs or not. These are all still deuterium-burning objects,
Yeah.
and they will be for a while. So I think I'm with Jeff in thinking it's probably has to do with the luminosity, which does provide your sort of dividing line there.